Quantum computing has always had this incredible promise, but it's also been stuck, held back by this one huge problem. Well, today we're looking at a brand new blueprint for a quantum computer that's completely different. And get this, the solution doesn't come from some fancy new tech, but from a mathematical puzzle that's been around for 250 years. So, to really get why this is such a breakthrough, you gotta ask the big question. Why are today's quantum computers so stuck? I mean, you hear experts talk about the NISQ era. That's the noisy intermediate scale quantum era. But what does that really mean? What's this great wall that's stopping us from building the powerful quantum computers we've all been waiting for? Well, it all comes down to the bizarre nature of the quantum world itself. See, the biggest problem isn't just making more quantum bits or qubits. Nope, the real challenge, the thing that keeps everyone up at night, is just keeping them stable. And this enemy, it has a name: decoherence. You have to understand, these quantum states are unbelievably fragile. I mean, the tiniest little vibration, a stray magnetic field, even a slight change in temperature, and poof, the whole delicate computation is just gone, wiped out. It turns into random, useless noise. And that, right there, is the single biggest challenge in this entire field. This creates this incredibly frustrating catch-22. Of course you want more power, right? And for that, you need more qubits. But here's the kicker. The more qubits you add, the more complex and tangled the whole system gets, and the more open it is to all that noise and all those errors. It's exactly like trying to build a bigger and bigger sandcastle while the tide is rushing in. The very thing you're doing to make it bigger is what's making it fall apart. So, what's the solution? How do you get out of this trap? Well, the proposal we're looking at today does something really clever. It doesn't just try to build stronger walls to keep the tide out. Instead, it completely redesigns the sandcastle from the ground up, using a blueprint. A blueprint that was discovered in the world of pure mathematics. And this journey starts somewhere you would never, ever expect. It starts with the solution to something called the Lichtenberg conjecture. This was a mathematical puzzle about these hidden patterns in numbers, and it's been unsolved for over 250 years. Just imagine that. Okay, so the first piece of this puzzle is something you might actually recognize from math class, Pascal's triangle, right? It's that neat pyramid of numbers built on simple addition. For what we're talking about today, let's just think of this as the matter side of the equation. It's the positive, constructive foundation. Okay, so you've got the matter. What's next? Well, the model introduces its perfect opposite, a subtractive, mirrored version of the triangle. So you can think of this as a kind of digital antimatter, designed to perfectly balance out the matter half. And here's where it gets really cool. When you take these two opposing forces, matter and antimatter, and you fuse them together at their tips, you create this completely new, beautiful geometric object, and it's called the Perez Hourglass. But this shape, wow, it's so much more than just two triangles stuck together. It's this unified mathematical object where all these deep, profound concepts just intersect. It's amazing. Tucked away inside its geometry, you find the Fibonacci sequence. You find connections to the super mysterious work of the mathematician Ramanujan. You find these deep, repeating fractal patterns. It's almost like all these fundamental truths of math were just sitting there waiting for someone to find the one elegant shape that could bring them all together. Okay, that's really cool. Beautiful math, for sure. But so what? What does a pretty shape have to do with quantum computing? Well, that is the crucial point. It's all about how this abstract geometry translates into a real-world physical advantage for a quantum computer. And this is a total paradigm shift. Think about it. Our current quantum computers are these super fragile systems that we are constantly trying to patch up with these incredibly complex error correction codes. It's a constant battle. But the hourglass architecture? It's completely different. It's born stable. Its very shape, its geometry, makes it inherently fault-tolerant right from the start. So how does it do it? It's actually genius. Imagine an error, a bit of noise, hits one of the qubits. The unique geometry of the hourglass acts like a channel. It naturally guides that error downwards, funneling it towards that narrow waist in the middle. And when it gets there, the interplay between the matter and antimatter halves causes the errors to literally cancel each other out. They annihilate. The geometry itself is actually draining away the noise. Okay, so that's the theory, and it sounds incredible, but does it actually work in practice? Let's jump into the simulations and see how this thing performs when it's put to the test. And the results from the simulations are, well, They're dramatic. Let's put the hourglass code head-to-head with a conventional method, something called a surface code, which is one of the leading approaches out there today. Okay, so we get a really powerful level of error correction. They call it a code distance of 21. Just think of that as a measure of how resilient it is. The hourglass needs just under 1,600 physical qubits. To get that same level of stability, standard methods would need way, way more. Like exponentially more. It's not even close. And it gets better. The simulations also showed this massive gain in performance. When they use a special technique called dual-rail encoding across both sides of the hourglass, they saw a 30% jump in something called fidelity. And all fidelity means is accuracy. It's how close your final answer is to the one you are supposed to get. Now, a 30% gain might not sound like a lot, but in this world, it's everything. It's the difference between success and total failure. Let me put it this way. Under the same noisy conditions, the hourglass system gives you an answer that's 92% accurate. A standard system, it barely gets to 63%. So basically, one of them actually works, and the other one is pretty much just giving you noise. And it's not just about stability. This architecture also makes key quantum algorithms run dramatically faster. Let's take Shor's algorithm. That's the one famous for being able to break most of the encryption we use today. On this new design, the number of steps it needs is just slashed exponentially. For the computer science folks out there, the complexity drops to O log squared n. For the rest of us, that's just a fancy way of saying that even when you make the problem way, way bigger, the time it takes to solve it grows incredibly slowly. It is a colossal speedup. So what does a speedup like that actually mean in the real world? The implications are just staggering. It means that breaking 2048-bit RSA encryption, the kind that protects so much of our digital lives right now, could actually be possible before 2035. And with a machine that has fewer than 10,000 qubits. I mean, that's a milestone that most experts thought was still decades away. And here's the best part. This isn't just some clever idea on a whiteboard or a cool simulation. This is a ready-to-build blueprint. There's a clear path to actually making this thing a reality. In fact, the roadmap is already laid out. Step 1, in the first year, is to prove the basic ideas work on the IBM quantum computers that already exist. Then, in the next couple of years, the plan is to build a dedicated 377-qubit machine by 2028 to demonstrate it. And the final step, a scalable 1,597-qubit processor by 2029. Yeah, that's the exact same size that performs so incredibly well in those simulations we just talked about. This is moving fast. It's just such a perfect metaphor, isn't it? This architecture takes the ultimate symbol of time running out, the hourglass, and turns it into a powerful tool for computation. I just love how the source material puts it. The sand is no longer falling. It is computing. So what this all means is that the era of truly powerful, fault-tolerant quantum computing, well, it might be a lot closer than any of us thought. The big question really isn't if we can build them anymore. It's what are we going to do with them? With this kind of power on the horizon, what are the first world-changing problems we're going to tackle? In medicine, in new materials, in AI? What do we solve first?